In this video, we're going to look at substitution for integration, also known as USub. This is section 1.5 in the OpenStax Calculus 2 book, but in the Calculus 1 book, it is 5.5. Now, as you know from my previous video, I do like to start Calc 2 where we finished and do a little bit of review from Calculus 1. So if you didn't have 5.5 in your OpenStax book for your Calculus 1 class, you would then pick it up in my Calculus 2 class, and we call it 1.5 in the Calculus 2 OpenStax book. Either way, let's go ahead and start. We're going to do a little refresher of the chain rule. Now, if you remember when we learned derivatives, where f is the antiderivative, capital F, and the inner function is g of x, that with the derivative of this function, f of g of x, it is the derivative of the outer function multiplied by the derivative of the inner function. And one of the ways that you may see this, you go from cap f prime to lowercase f g of x, and then multiplied by g prime of x. Now, if you learned it with u, like when we do du, e to the u, then when we learned this derivative, we know this is going to be e to the u, and you might have seen it as u prime. So if you learned it with a du of capital F u, then it is the capital F u, and then the derivative of u, or in other words, f of u multiplied by u prime. So when we integrate this, when we undo what we just did, which is this or this, then we know that when we undo this integration, when we integrate lowercase f g of x multiplied by g prime of x dx, it will give us the antiderivative of that composition of functions plus c. So here is the theorem. It says, basically, that if I can figure out what would be an appropriate u value, and I do that replacement, then I can do an easy integration of f of u du, which becomes the antiderivative capital F of u plus c. In other words, when I back substitute, I'm going to get capital F of g of x plus c. So here's a couple of things that you want to consider when you're doing the substitution. So typically when you see substitution, you think maybe this is an ideal one for substitution. We usually let the inner function, like the square root of something, and that something be my inner function. So this goes back to deciding what would be the best choice for the inner function and what would be the best choice for the outer function. So back in pre-calculus 1, when we learned composition of functions, we also learned how to decompose the composition of functions. And that's what this is all about, is choosing what would be the best decomposition of the functions and also what would be the best choice given what du would be. We then evaluate the new indefinite integral with respect to u, and of course, and we talked about this in my last video, that if there are limits of integration, you have one or two choices. Remember, option A or option B, and we'll go through that again in a little bit. So if I'm trying to decide how to integrate this, then I'm going to choose what would be a good composition of functions and what would be a good u choice. And when we first initially look at this example here, it seems a little bit overwhelming. You think, maybe I want to multiply this out, but you don't. You don't want to multiply this out. So if you look at just this portion of it, you have x squared plus 1 raised to the 4th power. Now, I ignore the 2x, and the reason I ignore the 2x is experience, and this is like something it's like playing an instrument. You're going to have to practice this to get good at it. So, and it's okay if you make mistakes when you first start out. If your first choice doesn't work out, choose something else. Now, again, the reason I'm going to choose this is because I see that the derivative of the inner function, so I'm going to say, hey, u must be my inner function, which is x squared plus 1. Its derivative, du, is equal to 2x dx. And here's that 2x. So that's what I'm choosing, my x squared plus 1 raised to the 4th power is my function I'm going to focus in on to decompose. So then if u is equal to x squared plus 1, then this can be replaced with u raised to the 4th power. So I come back to my integration, and what I like to do when I do my integration is I like to circle all of my replacements. So I know that this x squared plus 1 raised to the 4th power will get replaced with u to the 4th. And I know that this 2x and this dx, notice how I like to circle both of those, gets replaced with the du. Now what ends up happening is I take something that's potentially awful to try to multiply out and then integrate, becomes something really nice. It's just u to the 4th du. Now I just reverse the power rule. Now remember, everything I write in green really isn't there. I like to do that just as a reminder what to divide by and what the power should be. So this becomes 1/5 u raised to the 5th power plus c. Now, I started out with a function of x, so I have to replace, I have to back substitute. And my back substitution then becomes 1/5 x squared plus 1, because that was my u, raised to the 5th plus c. And that's my answer. So let's take a look at my next example here. My next example is, again, anything that's underneath the square root usually is a good choice for u. So I think that's going to be my u. So I'm going to say let u equal 3x squared plus x. And du is equal to 6x plus 1. Ooh, that's lovely. Multiplied by dx. And the reason that's lovely is this and this is a nice straightforward du replacement. So this becomes u raised to the 1/2 du, because I started out with letting u equal the thing underneath the square root, the value underneath the square root. And we know the square root can be wrote as u raised to the 1/2. So again, I'm going to go ahead and reverse my power rule. So I'm going to add 2 over 2, which is, in other words, I'm adding 1. And I'm going to divide by that 3 over 2. So this becomes 2/3, because remember, I am dividing by a fraction. So it means I'm multiplying by the reciprocal of u raised to the 3 over 2 plus c. And of course, I have to do my back substitution here. So 2/3. And my u, again, was 3x squared plus x raised to the 3/2 plus c. And there's my final answer. Again, what I'm going to do is I'm going to say, hey, what would be a good choice for you? Well, a good choice for you is not going to be just e to the 2x. Well, I guess you could do e to the 2x, but really, let's not do e to the 2x. What I'm going to focus in on instead is the exponent. Because remember, when we do the integration, or excuse me, the derivative, du of e to the u, this is going to be e to the u prime. So I think a good choice for my u is the x squared. Let u equal x squared. Du is equal to 2x dx. Now, I see an x, I see a dx, I don't see a 2. So I have to adjust, and I say 1/2 du is equal to x dx. And that's because I should have a 2 here, and I don't see a 2 here or here as a multiplier. So since I don't see a 2 there, on either one of those two factors, I'm going to have to adjust. And the way I do that is I divide both sides by 2. Now this x and this dx gets replaced with 1/2 du. So this function becomes, or this integration becomes the integration of 1/2 e to the u du. And that's because, remember, I don't have that 2 as part of my derivative of the original function, so I have to make that adjustment. Now we know that when we do the derivative of e to the u all day long is e to the u prime. Well, u prime in this case happens to be 1. And so this just becomes 1/2 e to the u plus c. Go back and do our back substitution. So we have e to the x squared, 1/2 e to the x squared, plus c is my final answer. On D, a good choice for D would be the denominator. So I'm going to say let u equal 10x minus 3. Du is equal to 10 dx. And once again, I don't see a 10 anywhere except for what I'm going to think u should be. So that must be in 1/10 du must be equal to dx. Now I replace this 1 dx with 1/10 du, and this becomes the integration of 1 over u multiplied by 1/10 du. So I'm going to bring this 1/10 out front, and I have the integration of 1 over u du, and this is the only time I'm not going to reverse the power rule. The reason I'm not going to reverse the power rule is because if you recall, u to the negative 1 plus 1 would mean that I'd be divided by 0, so I can't reverse the power rule. And in fact, I know that if I do the derivative du of the natural log of u, this is going to be 1 over u prime. Or in other words, du. So this becomes 1/10 the natural log, don't forget the absolute value, of u plus c. Now I have to back sub, and so I have 1 over 10 the natural log of the absolute value of 10x minus 3 plus c, and that's my final answer. Let's take a look at a couple of other examples here. In fact, I got a whole bunch of examples. It's just a whole bunch of doing some u substitution examples. And I want to really focus in on a couple of the ones. And one of the first things I want to focus in on this letter E here is sine to the 10th. Whenever I have sine and cosine, one has a power and one doesn't. The good choice is to let u equal the one with the power. So let u equal the sine of theta. Du is going to equal the cosine of theta d theta. So here's my du. Don't have to make any adjustments. And then this becomes u to the 10th. So this is the integration of u to the 10th du. Again, I'm going to add 1 and divide by that 11. And so I get 1 over 11 u to the 11th plus c. Doing my back substitution, 1 over 11, and I wrote 10. 1 over 11, the sine of theta raised to the 11th plus c, or you can write it as 1 over 11, the sine of raised to the 11th power of theta plus c. Either one is totally fine. Now, we take a look at this and we think, how are we going to do this? Well, we can just jump right in and we say let u equal x minus 2. And du is equal to dx. And you think, well, if I do that, I have this x left over. How do I deal with that? I know the of you are watching this is like, oh, I would do long division. Sure, you absolutely can do long division, and that's one of the ways that you can do this. The other way to do this is I can adjust this u is equal to x minus 2 to be u plus 2 is equal to x. And now I've got this replacement. I have this replacement and I have this replacement. So then this integration becomes the integration of u plus 2 over u du. And you're like, how did that help me? Well, it did help me. Because remember in algebra, basic algebra, if a plus b or a plus c over b, I can write this as a over b plus c over b. So I'm going to use that here. I'm going to say this is u over u plus 2 over u du. So I can write this as integration of 1 plus 2 over u du. Nice easy integration here. The integration of 1 is just going to be u, and then plus 2, and then it's 1 over u, so we know this is the natural log, the absolute value of u, plus c. Go back and back sub. Remember what I started out with was u is equal to x minus 2, so x minus 2 plus 2, the natural log, don't forget the absolute value of x minus 2, plus c. And I'll tell you what, you're like, hey, I've done all this and my homework keeps marking me wrong. The question I'll always ask you is, did you remember these absolute value symbols when you're doing the natural log? Because remember, you can't take the natural log of a negative number. So don't forget to put on the absolute value symbols when you put that in. All right, so let's take a look at G. And with G, we're going to do something similar. We're going to say, let u equal. Let u equal. I'm going to let it equal the denominator because it's raised to a higher power. So I'm just going to say let u equal y plus 1. And du is equal to dy. So I have this replacement, I have this replacement, and of course I have this u hanging out. So I'm going to do the same thing as I did before in my previous example. So I'm going to rewrite this u to be u, and I wrote y. U minus 1 is equal to y. That means u minus 1, the quantity squared, is equal to y squared. Now I've got all my replacements. This is going to be the integration of u minus 1, the quantity squared, over u to the 4th, and then du. Now this one isn't too bad to multiply out. So I'm going to go ahead and multiply out the numerator, and so I get u squared minus 2u plus 1 divided by u to the 4th, and du. And I'm going to use the same algebra like I did in my previous example. So I have the integration of u raised to the negative 2 minus 2u raised to the negative 3, and then plus u raised to the negative 4 du. And what I'm doing here is I'm doing u squared over u to the 4th. We know as u squared minus 4, which is where u to the negative 2 came from, and all the rest of them, just as a friendly reminder. And again, I am going to add 1 and then divide by that negative 1, add 1, divide by that negative 2, add 1, and divide by that negative 3. This then becomes negative u raised to the negative 1. The negative 2 and the negative 2 cancel, so then it's going to be plus u raised to the negative 2, and then minus 1/3 u raised to the negative 3 plus c. And don't forget to back substitute, so this becomes negative, and it was y plus 1 raised to the negative 1 plus y plus 1 raised to the negative 2 minus 1/3 y plus 1 raised to the negative 3 plus c. So I think you're probably getting the gist of it. Now I just want to talk about when I have actual limits of integration. So I'm going to look to see if I have one of the limits of integration somewhere. Oh, here we go. P has a limit of integration. I just want to say that this is in parentheses. Okay. So I just want to look to see if there's anything else that is interesting. Again, nice little adjustments here. And what I mean by that is if I let u be the value underneath the radical, so 3x plus 2 and dx, and then du would equal 3 dx, so 1/3, and du is equal to dx. So this gets replaced with 1/3 du. This gets replaced with u raised to the 1/2. And you're thinking, okay, I have this x here. Oh, and I shouldn't have this dx right here. I have this x here. I have x plus 1, so you make the adjustment. You say, oh, u minus 2 divided by 3 is equal to x, and that's this replacement. So then this becomes u minus 2 divided by 3 plus 1, and then I'm not going to finish this, I'm just going to write it all out. So this is going to be u minus 2 divided by 3 plus 1, multiplied by u raised to the 1/3, multiplied by 1/3 du. And what I would do is I'd factor out a 1/3 out of these two, distribute the u to the 1/3, and then factor this 1/3 out as well. And then you have a nice integration. And let's just take a look at h here. And with h, I would be tempted to try to clear e to the negative x. And it's okay if you start down that road. You're going to actually find that it gets super messy super fast. So rather than that, let's just say let u equal the denominator. It's usually a good choice to start out with. E to the x plus e to the negative x. Du is e to the x minus e raised to the negative x dx. Ooh, this is nice. So this gets replaced with du. This gets replaced with u. And so my integration just becomes 1 over u du. And so I'll let you finish that off. Similar to j, k is another one that you would probably let u be the denominator. Let u equal, and I wouldn't write it as cosine cubed, I'd write it just as the cosine of x, because I know the derivative of cosine x is negative sine x. IJKL is similar. M is, M is not quite what I would expect. M is like, how would that work? Well, you can still do this with a u sub, but this actually looks a lot like, if I factor this 3 out and I have 1 over, 1 plus, if I were to write this as 5y, the quantity squared, dy, and you're thinking this is supposed to be in the u sub. Yeah, this actually kind of looks like the inverse tangent is what it looks like. So because we know that if I do d du of the tangent inverse of u, this would be 1 over 1 plus u squared times u prime. Oh, so I guess I kind of do have a u sub, except for it's just going to be let u equal the 5y. Du is equal to 5 dy. And you can see I don't have that 5 there, so I need 1/5 du is equal to dy. Now this gets replaced with u. This gets replaced with 1/5 du. So in other words, what I have is 3 over 5, the integration of 1 over 1 plus u squared du, which we know becomes 3 over 5, the tangent inverse of u plus c, which is 3 over 5, the tangent inverse of 5y plus c, and that's your final answer. Now, what I wanted to do is I wanted to get down here to p, because this is one of those ones, and we talked about it in my previous video, but what happens when you have limits of integration? There are two options. Option A, so I'm going to do it with option A, which is replace x equals 0 and x equals 2 with the appropriate u value. So it's u equals and u equals. So I'm going to do it two ways. So I'm going to let u equal, again, the denominator, not the squared part, so x squared plus 1, and du is equal to 2x dx. So we know this gets replaced with a du, no adjustments are needed, and this gets replaced with u squared. So then my integration is going to be 1 over u squared du. Now notice I didn't put my limits of integration. With option A, when x is equal to 0, I'm going to put 0 in right here, u is going to equal 1. So I've changed my limits of integration. When x is equal to the upper limit, which is 2, u is going to be equal to 2 squared plus 1, which is 5. Notice I changed my limits of integration. So I'm going to go ahead and integrate this, and I'm going to rewrite this as 1 to 5 of u raised to the negative 2 du. I add 1, divide by that negative 1. And so I end up with negative u raised to the negative 1, evaluated from 1 to 5. So negative 5 raised to the negative 1 minus a negative 1 raised to the negative 1. So negative 1/5 plus 1 is 4/5. That's option A. Now, I'm going to do option B. And replace 0, x is equal to 0, and x is equal to 2 with u1 and u2. So I'm going to use u1 and u2. I'm still going to integrate, and I'm going to end up still doing the same u sub, and I'm still going to have u raised to the negative 2 du. And this is going to give me negative u raised to the negative 1, u sub 1, u sub 2. And this, if you choose this option, totally fine to do this. I'm not a fan of it. You have to back sub now. You have to have these dummy variables as placeholders, and then you have to back sub. If you don't put these dummy variables here, or if you leave it as 0 and 2, that is mathematically incorrect, and I will mark you wrong because it is not correct. Totally fine to do this, however. So now you have negative, and then it was x squared plus 1 raised to the negative 1, and now you go 0 to 2. You're going to get the exact same answer. Personally, I like to change my limits of integration right out of the gate so that I don't have to do any back substitution. I remind myself to back substitute. I remind myself to put dummy variables there. Okay, here's a couple of more with the change of variable. I think I'm going to do Q. Q looks interesting. I don't know why I didn't put parentheses on that. I think Q is going to be the most interesting. So actually, I think R might be interesting. So with R, you think, how am I going to write cosine squared? Well, you're going to open up your 2-page trig formula sheet, and you're going to think, power reduction formulas. Cosine squared of 8 theta can be replaced with 1/2, 1 plus the cosine of twice that angle. And that's how you're going to do that one. That's a power reduction formula. And then your u sub is going to be this angle here if you end up doing a u sub. Don't forget power reduction formulas. You're like, what? That's pre-calculus 2. We're actually going to do more of that later in calculus 2. But I just want to refresh and remind you that we have these power reduction formulas. It is on that 2-page trig formula sheet that I give you for every test. And then it's just a whole bunch of nice integrations here. Ooh, look. Darn, look at that power reduction formula I'm going to have to do, and I have to do it twice. So you're like, what? So sine to the 4th theta is the same thing as sine squared of theta, the quantity squared. There's a power reduction formula for sine that is 1/2, 1 minus the cosine of 2 times my angle theta. And then this thing gets squared, and you're like, what? Yeah, it's a power reduction formula twice. Who doesn't love that? And a good choice for you would be let u equal the x squared minus 2x. And du would be 2x minus 2, which is almost this. You just have to divide both sides by 1/2, or divide both sides by 2. In other words, multiply by 1/2. Don't forget your dx. I just get so excited I forget my dx sometimes. And so this becomes x minus 1 dx. So you can see that substitution there. Again, a good choice for you would be the denominator not including the square root. Good choice would be cosine here. Good choice would be the denominator, not the square root part. Good choice would be the denominator, not the squared part. Anyways, you get the gist of it. Now, I'll leave you to it at this, and we'll go over any of the ones you want to in class, and that's it for this video.